When mathematicians track orbits in discrete chaotic systems over infinite time horizons, they run into a computational wall. Eventually, most paths collapse into loops. These are standard periodic orbits. Once a system enters one, it repeats the exact same sequence of states forever. The future is entirely predictable. But the symbolic branch collapse program contains a specific anomaly. When an orbit is seated at a dyadic rational, it breaks away from the loops. It marches in a straight line, generating a unique state at every single step. Proving that this path never eventually repeats is a massive mathematical challenge. You cannot simply run a simulation to infinity to check every future state, because computational power has physical limits. To bypass the need for infinite computing, we have to look past the simulation. We need an absolute structural proof embedded directly in the arithmetic of the system. That structural proof exists within a specific mathematical environment, the mixed piecewise affine return map. Bounding the state space here is notoriously difficult. The system operates on alternating sets of rules, driven by fluctuating parities and branch choices that throw the outputs in wildly different directions. This equation is the core of Theorem 4.1. It dictates exactly how a state transitions after one complete cycle through the return map. Structural aperiodicity in this map is driven entirely by a simple, unbreakable arithmetic ratchet within this exact formula. The ratchet works by enforcing a single rule. The exponent in the denominator must continuously, relentlessly grow. We begin with the starting condition, the dyadic rational state y, represented as the fraction q over 2 to the power of m. This fraction must be in lowest irreducible terms. Therefore, numerator q is an odd integer, and exponent m is at least 1. We feed this initial state directly into the one-period return map. After exactly one mathematical jump, the system outputs this expanded fraction. The fate of the entire orbit rests on one question. Is this newly generated fraction already in its lowest terms, or can factors of 2 be cancelled out from the top and bottom? To find the numerator's parity, the first term multiplies odd integers, so it is inherently odd. The second term contains 2 to the power of m, making it explicitly even. Subtracting this even integer from the odd one guarantees an odd final result. Through pure algebraic constraint, the entire numerator resolves to an irreversible odd value. To understand why that matters, we use lemma 1.5, which defines the two-adic valuation metric. It measures divisibility by counting how many times an integer can be cleanly divided by 2. The rule is strict. A term with the exact lowest two-adic valuation cannot be cancelled by adding or subtracting terms with a strictly larger valuation. Placing our definitively odd numerator back over the even denominator of 2 to the power of m plus p reveals a strict boundary. The odd numerator contains 0 factors of 2, making mathematical reduction impossible. Thus, the new denominator's exponent remains exactly m plus p. In just a single, irreducible step, the denominator's exponent has strictly grown from m to m plus p. We can now transition this single application of the return map into an infinite sequential induction loop. Because guaranteed irreducibility is locked in at every iteration, every successive step adds exactly p to the exponent of the denominator. After k total iterations, the denominator's valuation is explicitly m sub 0 plus k times p. Because the phase count p is strictly greater than 0, this exponent climbs endlessly as iterations approach infinity. This relentless addition forces the physical addition of the denominator to scale up exponentially over time. A continuously growing, irreducible denominator guarantees that every output fraction generated by the system has a larger base than the one before it. This mathematical reality dictates the physical path of the dynamical state. Distinct fractions mean mathematically distinct physical positions. Because every state is unique and the denominator is strictly larger every time, the orbit can never loop back to intersect a previously visited state. Furthermore, a fraction tethered to an infinitely growing denominator can never resolve to the integer 0. This fulfills the requirements of the symbolic branch Collatz program. It proves orbital injectivity entirely through arithmetic, skipping the need for bounding state spaces or empirical simulations. In this mixed system, infinite complexity is perfectly governed by the unbreakable mechanical certainty of two-adic denominator growth.